Hello, everybody. So now we're continuing the session. And what we're going to do is hypothesis testing. Okay. Again, this is very, very important. We just covered point estimation and confidence interval. And this is kind of the third fundamental statistics thing that we got to do. It's called hypothesis testing. Okay. So all this lecture is very, very important. Very, very important. Okay. So make sure you follow through, because all these methodologies are used later in statistics. Okay. Okay. So the T and Z, this is hypothesis tests. Okay. That's what we're going to be doing today. In hypothesis testing, I'm trying to see or hypothesize if a parameter of a population distribution, like its mean or variance, is some particular value. So I don't know the population, I don't know its mean or variance. I'm trying to hypothesize whether it's a particular value. Okay. There are two types of hypotheses. Under the null hypothesis, I believe the parameter is a particular number. Under the alternative hypothesis, I believe the parameter is not that particular number. Okay. For example, suppose the population is a die row, call it X, that I do not know the distribution of. In this case, call the expected value of it mu. Suppose I want to test whether its mean is 3.5. So there's two hypotheses I'm testing. The null hypothesis, whether the mean is 3.5, or the alternative, whether it's not 3.5. Okay. If I think the die is fair, I would want to support the null hypothesis. If I think the die is not fair, then I would want to support the alternative. In any case, I will need to gather data and actually test these hypotheses. Okay. I would first gather the data, and we'll call it data sample. And using the sample data, I can compute the sample mean from the data. This is called the point estimate. And if that is considerably far away from 3.5, then I will reject the null hypothesis and favor the alternative. Okay. So how far is too far? If the sample is pretty small, say I roll a die twice and get a point estimate mean of 4.5. This might still be a reasonable value, and the die's mean mu might still likely be 3.5. Okay. But, however, if the sample is very big, say I roll the die 1,000 times, and I get a mean of 4.5, then I'm pretty sure that mu is very close to 4.5. So I will actually reject the null hypothesis that mu is 3.5. Okay. Okay, so maybe in this case the die is not fair if I'm getting a mean so high. Because okay. So here's the traditional kind of Z test. And sometimes this is also called the T test. Sometimes people use Z test or T test. I'll show you the difference in the next week when we do it. I'll show you why there is this difference. But how is this basically tested? Again, there's the null hypothesis and the alternative hypothesis. When testing both hypotheses, the actual test always tests the null and sees if there is enough evidence to reject it. If the test passes, then I say I retain the null hypothesis. If the test doesn't pass, then I reject the null and favor the alternative. So the first test is the traditional Z test. And here's how it proceeds. You suppose that the mean is indeed 3.5 to begin with. Then I can get a distribution of a sample mean. This is all possible values of the point estimate, x bar, around 3.5 as well. If the actual computed point estimate is significantly far away from 3.5, or I get an X bar that's very far away from 3.5, then it was very unlikely that the point estimate was taken from a distribution of X bar centered at 3.5. Therefore, I reject the null hypothesis. Okay? Okay? On the other hand, if X bar, okay, is close to 3.5, then I retain the null hypothesis. Okay? Okay? So let's just right here. Okay, I retain. Okay. Assume that, okay, so how do I know if too far is very far, right? Assume that mu is 3.5 and see where the estimate of X bar is located on the distribution of X bar. Again, if it's very far away, I reject the null. So, convert X bar to Z random variable to test this. In this case, compute Z is X bar minus 3.5, the hypothesized value, over sigma divided by square root of n, over the standard deviation of X bar. Okay? And so with data, I can compute the point estimate of X bar and S and obtain a value for Z. With the data on Z, it's no longer a random variable, and it's not called a realized Z value. A Z score, a test statistic. So Z value, Z score test statistic is now known Z. Test to see if Z is beyond the cutoff point or lower than the cutoff point. Recall that, again, Z alpha over 2 are cutoff points based on the significance level. Okay. If so, reject the null hypothesis in favor of the alternative if it's beyond the cutoff points. If it's within the cutoff points, I'm going to retain the null hypothesis. Notice that the lower the sigma, the more extreme, the larger the critical value, and so it is hard to reject the null. Okay? Okay, the bigger this confidence level, it's hard to reject the null hypothesis. Okay? And the lower the significance level. Alpha here represents the probability of rejecting the null hypothesis, even though it is true. Okay? It is the significance level. Recall. Recall. 1 minus alpha is the confidence level. So if I tell you the significance level, you know the confidence level. If I tell you the confidence level, you know what the significance level is. Like this, okay? 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 So, how would you interpret the results? And I talked about this already. Again, suppose, for example, okay, you roll a die 20 times, you get a sample size of 20, you get a sample mean from those 20, it's 4.5. But you hypothesize if the die is fair. You want the mean to be 3.5, maybe. You're trying to see, is this fair die or is it not fair? If, based on the z-test, the 4.5 is outside the cutoff points, now I have to convert the 4.5 into a z value. Okay, I have to transform it, right? Therefore, if it's outside the cutoff points, I reject the null and accept the alternative. Okay. I can also say the following: the sample mean of 4.5 is significantly, you're supposed to say significantly different than 3.5, or statistically significantly different than 3.5. Okay. If based on the z-test, the 4.5 inside the cutoff points of critical values, I retain the null hypothesis and reject the alternative. I can also say the following: the sample mean of 4.5 is not significantly different than 3.5. Okay. Okay, so this was how to do the test using the z-test, the z-test or the t-test. Okay. Now there's also something called the p-value. The p-value is defined as the probability of getting a point estimate of x bar or z-value more extreme than what was actually computed, given that the null hypothesis is true. The p-value represents area to the right of the z-value times 2, or area to the left of the z-value if it's negative times 2. For example, if x bar has corresponding z-value of 1.95, then the p-value is 0.05. Okay? As a test, one can use the p-value if the p-value is greater than alpha. Okay? Then I know the z-value is lower than the cutoff point. And so I retain the null hypothesis. If the p-value is less than alpha, okay, then the z-value is outside the cutoff points, and so I reject the null hypothesis. Okay. And lastly, last but not least, is to check whether the hypothesized value is in the confidence interval. For example, does my confidence interval of mu include 3.5, my hypothesized value? If my if 3.5 is inside, then I retain the null hypothesis. If 3.5 is outside the confidence interval, I'm going to reject the null hypothesis. Okay. 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 The next topic here is one-tail tests. So far in the confidence interval, especially we did these two-tail tests, but sometimes you can have one-tail tests. In one-tail test, I'm interested in testing whether the mean is greater than or equal to some value, or less than or equal to some value. A lower tail test considers only the left side of the distribution. So I can reject if my x bar is significantly lower than my hypothesized value, but I cannot reject the null if I get an x bar that's much bigger than mu. Okay. Okay. At alpha equals 0.5 significance, there is one cutoff point, and now negative z alpha, so that only 5% on the left side is not covered. Okay. And vice versa for an upper tail test. Consider only the right side of the distribution. Okay. So suppose, okay, like this, I'll show you here. Okay. Okay. H naught, mu is less than mu naught. HA, mu is greater than mu naught. So I can only reject if I get a very big value of my in this case of my test statistic or my sample mean. Okay. At alpha equals 0.05 significance, there is only one cutoff point, n is now z alpha, so that only 5% on the right side is not covered. P-value still holds as an area to the right or left of the z-value. However, it is no longer multiplied by 2. Okay. Okay. What is a type 1 error and what is a type 2 error? A type 1 error is that the null hypothesis is true, but the null is rejected. And the probability of type 1 error is level of significance. Generally, if the level of significance is 0.05, there's a 5% chance that the null hypothesis is true, but it is rejected. Okay. What about a type 2 error? That the alternative is true, but the null hypothesis is retained. To compute the probability of a type 2 error, you need to know the exact distribution of the population random variable. Notice the probability of a type 2 error is 1 minus alpha if the actual population mean is just slightly different than the hypothesized. Slightly different, okay? To minimize this error, increase sample size, okay? So distribution of sample mean is very tight, okay? Okay. So to minimize this error, because you can, if you get close values of x bar, right, to your mean, you're always going to retain the mean, pretty much, okay? If your sample size is very small, okay? But as your sample size gets larger, you know what happens to the variance of x bar? It collapses, right? So you're more likely, in this case, to reject as your sample size increases. Okay. Okay, so let's take a little break now, and we'll do the problems next. Actually, we'll try and do the problems now. Next, I'll discuss what I just said with graphs. Okay. Hello, everybody. So let me just show you what this hypothesis test is all about. Okay, I'm going to show you graphically so you understand. Okay. Anyways, suppose there's a population. It looks something like this. Okay. Like this maybe. I don't know how it looks like. Okay. So, something like this. We'll call the population, it's a random variable, we'll call it x. It's some kind of an unknown distribution. Okay. And this population has some kind of a mean, mu. I don't know what this is. It could be 5, 10, 100, I don't know. It just depends where the location of the random variable is. Okay. Is this mean? So expected value of x equals mu, and has some kind of a variance as well, and some kind of a standard deviation as well. Okay, so the variance of x, we'll call it sigma squared, and the standard deviation of x, we'll call it sigma. Okay. It turns out that when I grab a sample from this, I grab some kind of a sample, okay, and in particular, I compute x bar, which is the average of the sample. Again, I treat the sample as unobserved, so I can get probabilities for x bar. I can get all possible values for x bar, or what it could be. Okay. Obviously, if the sample is very big, x bar will be very, very tight around the mean here. Okay. So I'll have high probabilities of getting numbers of x bar. This is the distribution, I'll say, of x bar. Okay. I'll get high probabilities of x bar getting pretty close to the mean here. Okay. And in particular, x bar, I know it's normally distributed with a mean, the same mean as expected value of x, and variance sigma squared over n. It's the variance of x divided by n. So notice, as my sample size increases, x bar is going to be tighter and tighter around mu. Tighter and tighter around mu. So the x bars that I will be getting will be very, very close to mu. Okay, the possibilities of the x bars, a lot of them will be very, very close. Okay. And so this is where hypothesis test comes in. I suppose that mu is some value, my hypothesized value. I call it 10. Okay, I call it 10 like this. Okay. Okay. And so I suppose it is 10. Notice I can kind of pinpoint this X bar. I know its shape, and I know I can say how spread out it is also, but I don't know its location. So if mu is 10, again, mu is the expected value of X. It's also the expected value of X bar, mu. Okay. But if mu is 10, that means X bar will also have a mean of 10. Okay. Okay. Then I see, suppose I get a number somewhere, I don't know, like let's suppose I get a number of 10 and a half for X bar, of 10 and a half, and the number is somewhere here. Oh, this seems like a reasonable value. If my true mean is 10, which I don't know, and I get an X bar of 10 and a half, the 10 and a half seems like a reasonable value. Okay, it's somewhere here in the distribution. Okay, and it's not something that I wouldn't expect to get if my mean is 10. I can get other extreme values that are more than 10 and a half. I can get 11, 12, 13. These are all possibilities. And I can also get maybe numbers like 9, 9 and a half somewhere here. Okay. And so these are all reasonable values of this X bar. However, if I'm getting an X bar, let's say at 20, somewhere here, okay, then I say, hey man, this is probably not a reasonable value. Getting a number like 20 and more extreme than 20, let's say this is probability of getting something that's more extreme than 20, this I'll say is kind of a 1% chance only. And getting something more extreme because of symmetry, I'll call 0 here. Getting something in the negative numbers, because this is like 10 is the middle, so 0 is one side, 20 is the other. Okay? So getting something less than 0 is also a 1% chance, maybe, okay? So I'll say getting a number like 20 is rare. It's rare to get this kind of a big number, or a very, or a negative number. This is kind of a rare case. If the population mean is mu, and I'm just getting an X bar. It can happen, yes, it can happen, but it's going to be very rare, okay? And then because it's so rare to get a number like 20, I say, man, probably the mean is not 10. It might be closer to 20 somewhere. It might actually be higher than 10. And so what I say is, because I'm getting such an extreme number, such an unlikely number from X bar, I'm going to, what am I going to do? Reject the null hypothesis that the mean is 10, that this population mean on X is 10, okay? Because my X bar is 20. It's so big. It's not reasonable, okay? Now, if I get numbers like 10 and a half, 9 and a half, oh, they seem to be pretty reasonable here, so I'm going to retain the null hypothesis, okay? So this is all what this is. And again, there's a few different tests. The first one is the, and I'll talk about it, okay? Okay. So this is the whole kind of story behind this hypothesis tests. Okay. Now, I know the distribution of x bar. If you tell me the mean, in this case, if you tell me it's 10, for sigma squared, I'll give you s squared. This is the sample variance divided by n. I know n, so I can get you an exact distribution here, and I can compute exact probabilities, how extreme 20 is. Is 10.5 extreme or not? I can give you the exact size of this, okay? Or an approximate size at least, okay? Of this x bar distribution. And so the whole idea now is that I need some kind of a calculator to tell me probabilities and areas. That's what I need. And then I'll be able to tell you if 20 really is extreme or not. Okay. So what better calculator than to convert to the standard normal. So this is what the test actually does. Okay, it converts to the standard normal, so you can use the probability tables. Okay, that's why it's called the Z test. Okay, so I have this x bar distribution. Let's say it's centered at 10 for simplicity. I get a number like 20 here, and I get a number like 0 here, okay, or something like this. And then I want to convert this into the Z. This is the Z test, okay? I convert it into a Z distribution. Now this is going to be 0 here, all right? So the 10 corresponds to 0. The 20, I don't know, it might correspond to some other number. What is the conversion formula? You guys remember? It's like this: Z equals, if you remember what it is? Well, I remember, okay? It's the variable x minus expected value of x. So x is just some random variable, okay? That's a normally distributed. And that's here a standard deviation of x. Okay? In our case, what is my x? It's x bar. Okay? X bar like this. Okay? My expected value of x is what? Is mu naught, or 10 in this case, okay? In this case, the standard deviation of x is just s over square root of n. So I have the formula, I plug in the formula, and I convert. Let's suppose I plug in 20 here. I know s, I know square root of n. It spits out a z. Z is like 2. Okay? If z is 2, guess what? I have some cutoff points here. I have some cutoff points here. This is like 1.96, this cutoff point, if what's inside is 0.95. If you remember from previous. This is 1.96 for 95% confidence. This is negative 1.96. So if I get something like 2 or greater than 1.96, this is rejection region here. So I'm going to reject the alternative, right? And this is 1.96 here. The 20 corresponds to the 2, probably, okay? Okay. I don't know. It depends on this on the sample size and the standard deviation, okay? Okay, so this is the whole idea behind this hypothesis testing. And you can also do it with a p-value. Again, you need to convert, but the p-value will tell me the following. Again, this is the z. Let's say this is, I get a negative 2. That will correspond to 20. This is called a p-value. And the p-value states, oh, okay, calculate the probability of getting something more extreme. See if it's bigger or less than, sorry, it's positive 2, this is 0, and it's negative 2. Okay. See if the probability of getting something more extreme, this plus this, if p-value, in this case, is less than the significance, alpha, then what happens if it's less than? Reject null hypothesis. Normally, when you do statistical tests and when you use these statistics, you want to reject the null hypothesis. You want to reject this. Okay? So you just have to see. And always, whatever with a cutoff point in a z-test, if I reject this test, I'm also rejecting the z-test. They're all equivalent, okay? They're all equivalent. Okay. Okay, so let's just do some problems really quickly, okay? Okay, like this. I'll do some problems, okay, everybody? We'll just do one problem, but it's a big one. Okay, so I have a sample, 624, 645. And this is my sample S, okay, like this. And the first step is what is the point estimate of the population mean? The mean of the distribution of the die roll, the point estimate. This is X bar in this case, okay? Or is the sample mean? This is the sample mean. So with the point estimate, what I'm going to do is I'll just compute X bar. And this is the sum of the x's divided by n. So let's just do the math really quickly. Okay, I get a 4.5. Okay. The next step is, so based on these die rolls, if somebody asked me, hey, what do you think? Is this die fair or not? What is your best guess? What is your best guess for the population mean of the die roll? And I'll say, man, my best guess is that it's 4.5. Now, could it be fair? Yes, but my best guess is just based on my sample, not what I thought before or anything like this. Just based on the sample, my best guess is 4.5 of a sample mean. Okay, so it's a bit high. The numbers are a bit high. So my best guess is that it's not fair, just based on the sample. Okay, but I can give you a high probability interval where the population mean will be. Okay, and this is the confidence interval. Okay, an 80% confidence interval. And if you remember, let's write the formula here. Okay, this was X bar minus some number. The number is Z alpha over 2. Okay, S over square root of n. And then mu is here, and it's x bar plus this number. Like this, okay? And this is equal to 1 minus alpha, where this is my level of confidence that I pre-specify. Okay? So x bar is this. What is 1 minus alpha? Is 0.8. Alpha is 0.2. This is the significance level. Okay? I specified this in the problem. I gave you 1 minus alpha. Okay? Then, what is the cutoff point? I computed this in the previous video lecture. In this session, I computed this also, right? It was 1.28, if I remember right. Okay? 1.28. These are the cutoff points, so plus minus 1.28. Okay? Then what do I need? I need S. So square root of n equals, there's 6 numbers, so square root of 6. This is the amount of numbers. And last but not least, let's compute S. S. How do you do it? You subtract each one of them from the mean and you square them. I'll give you a shortcut. I do the subtractions in my head because the mean is 4.5. So how do I do it? I do the first number here. 6 minus 4.5 is 1.5. I do this in my head. So just to save on the writing. So 1.5 squared. Okay? The second number, 2 minus 4.5 is 2.5 squared. Okay? Okay? Plus the third number, 4 minus 4.5 is 0.5 squared, because everything gets squared, so it doesn't matter if it's positive or negative, the difference. Okay? Plus, again I have 6. 6, again I have 4. Okay? And last, again I have 5 minus 4.5, again it's 0.5 squared. Divided by, how much do I divide here? By 5. And this is s squared. Okay? So just do the math real quick. Okay? Okay, I get 11.5 over 5. So this implies that S, let's just write it like this, S, okay, S equals to square root of 11.5 over 5, which equals to what? Okay, 1.52. And what do you do then? You have everything. You have X bar, you have this is 1.28, 1.28, S, you have 1.52, and square root of 6. You can just leave it like this. This is square root of 6 is 2.44, 2.45. Okay? And so what do you get at the end? Just do the math and let's see if you get these results, okay? Okay, this is the numbers I got. This is equal to 0.8, or let's put it here, 0.8, okay, like this. So this is an 80% confidence interval. Okay, moving on now. Okay, last but not least, you can do a hypothesis test. So let's just do a z-test for now. A z-test. Okay. Okay, everybody. And again, what is the basic idea? Is that okay? I got some die roll distribution there. I took 6 different numbers. So basically, I need to convert into the z value. Okay. So that's x bar minus mu naught over s over square root of n. It's 4.5. 4.5 minus 3.5 here, tell you this. And it's 1.52. And that's, square root of 6. Okay, I'll just leave a square root of 6. And guess what you get? Okay. $1.61. $1.61. Okay. Basically, what is this? This is the z value. The z cutoff point is plus minus 1.28. These are the cutoff points. So on my distribution here, I have z and this I have here, right, 1.28, and here I have 1.61. Since z equals 1.61, okay, greater than 1.28, implies reject the null. At you can say 80% confidence level. Okay. You can also do it with a p-value. So what is the p-value of me getting something? The probability of me getting something more extreme and me getting something less extreme than negative 1.61. What is the area? The black areas here. This plus this. And so you just come here and you look at negative. This is another one of the z tables I'm going to post. But you look at where the z is negative 1.61, and negative 1.61 should be this one. And the precision is right here on top. So negative 1.61 is 0.0537. So the area here is 0.0537. And that implies by symmetry, the area here is also. Like this, okay? So the total, this is separate now, okay? So p-value equals 0.0537 times 2, which equals 2.10. Let's not make any errors. 74, I think. Okay, 74 like this. Okay, and its p-value in this case, you know, alpha here. Alpha, again, 1 minus alpha is 0.8. This is like the confidence level. And this is in percentages. Okay, but 1 minus alpha, or the area in the middle here, between the two cutoff points, okay, is 0.8. This is 1.28, a negative, okay? And the area to the right is a significance level. So alpha equals 0.2. So the area to the right here is 0.1, and the area to the left of negative 1.28 is 0.1 also. So the total is 0.2. Anyway, the p-value, in this case, it's smaller than 0.2. Okay, 0.1074 is smaller than 0.2, which equals alpha, the significance level. Okay, then it also implies I reject the null hypothesis. Okay. Okay. So moving on, and lastly, if you remember our confidence interval, it did not include wait a minute here. The confidence interval, it should be 0.8, not 0.95. It should be 0.80 for 80% confidence. And lastly, the last test is just to see, is 3.5 in the confidence interval? In this case, 3.5 is not in the confidence interval. Okay. Therefore, I'm going to reject the null hypothesis if it's not in the confidence interval. Okay. 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 And lastly, so this was the confidence interval way. If it's in the confidence interval, I'm going to retain the null hypothesis. These are all this is the same thing. Okay. Okay. And you can read on your own here. Test 4 is if I don't want to convert into the z distribution, I can just get the distribution of x bar and see how far away 4.5 is. If it's in the cutoff points or not of x bar. I can compute probabilities right there. Okay. Okay, the 90% confidence. Okay, everybody, do you guys have any questions on this? Okay, so please do the next problem before class. It's this one here. So now for the 90% confidence here, okay? And I'm asking, do you reject the alternative at the 95% confidence level, the 0.05 significance level, okay? So try to do this problem on your own for next class, okay? Bye-bye.